paper was by Bowen and Holden, and it says the shear instabilities of a mean longshore current. What's interesting is that even though it's talking about longshore current, what's actually more embedded in this is infragravity waves, which is why it's really good, for us to discuss this now. The objective, I'm going to read this, I hate reading from slides, but I did write this, so. They determined a theoretical model for far infragravity, or FIG, as I'll call them, waves, based on the conservation of potential vorticity using alternate solutions to the equation of motion. Now, I want to point out, just like the big picture here, what they're trying to do is make an analytical model, so a mathematical model for this thing that's going on with these longshore currents that's basically being caused by far infragravity waves. So big picture, they're trying to make an analytical model, and they're using some data that they collected from the superduct experiment back in '89. So, and they used, for the comparisons, they're using phase velocities, wavelength, and timescales, which will only go into that those diagnostics a little bit. I try to find a little bit of background information on the superduct experiment because I'm thinking, well, there's a lot of these experiments that Scripps have done that have stuff posted. The only thing I found is this. I'm not sure how accurate it is. So anyway, it was pretty lame. So, not to steal a slide, but I stole a slide. Infragravity waves, the background.
Not properly cited, I know.
So the big picture of infragravity waves I wanted to point out with this slide is these trapped edge waves, which based on this being a longshore current, what we talked about the other day is that you have these, under certain specific conditions, you get these trapped edge waves that almost act like a, that almost act like a shelf wave. And then you have, of course, your leaking waves. But that I wanted to kind of focus on that because this paper, it really goes into a phenomenon that happens. It's not exactly a trap wave, though. So again, so looking at this is our infragravity spectrum. Touchdown. So infragravity spectrum here, they're looking at far infragravity. So I want you to give you kind of idea about that 5-minute period here. What this is, what this paper was looking at specifically. And a little bit of information about what, the far infragravity waves. So something exactly what Chris stated is this energy along the longshore direction that they noted in this other paper. So it seems like when the energy comes in from these infragravity waves, it transfers along the longshore direction. And they noticed that for these far infragravity waves, their wavelengths are about twice the width of the actual longshore current itself. Remember this, the wavelength is twice the width of the longshore current. So the energy is linked to the strength of the longshore current, so there's a direct link there. And the big thing is they don't satisfy the gravity wave dynamics, which is why they're coming up with this mathematical solution. The so what? Like why do they even care? So they create these perturbations in the longshore current that creates these other things called vorticity waves. So the vorticity waves are kind of like these edge waves, really. But the only real, I guess, difference is that they're, the basis for them has vorticity. So anyway, so but what these do, before this event was attributed to longshore friction. So what they're basically, their concept is that, well, we're attributing this event that happens in the longshore current, these perturbations in the longshore current, which I'll show you on the next slide, are happening because of the potential conservation of potential vorticity and not just because of the bottom friction. So again, they want to seek a model that works. And one of the other big things, like the so what reasons, is that it actually increases longshore mixing. And they say that in some circumstances, it can be 10 times of what incident waves create, which is significant, especially if you're a fisherman. Alonzo's not here, but he'd love that. Okay, so this is one of the slides. So this kind of gives you a big picture of it. So what we're looking at here on this side is the stream function. And again, this takes me right back to a shelf wave or these edge waves, is that you actually have low and high pressure system, the high pressure areas that are created, which they're saying basically by these infragravity waves. Had it not been for these infragravity waves, you would see this longshore current that just pretty much flows straight. Or if you look at this velocity profile, you just see arrows going right up for a longshore current. But what they're basically saying is there's actually a potential vorticity that is created by these infragravity waves condition that is creating this these areas of what they call where it just gets weaker. And actually it looks like it just kind of causes it to snake up and down the shore, kind of like what we saw on the edge waves in the other slide. There's questions. What is the restoring force of a vorticity wave? Any ideas?
Stress.
Gravity?
Not no, because it's an infragravity, so it's higher than gravity.
Coriolis.
Surface tension?
potential vorticity. It's actually almost a trick question. It's a so they use potential vorticity, and the concept is that the longshore current itself, because of the fact that so you have a longshore current, you have this infragravity wave that comes in. The longshore current creates a background vorticity, and I'm going to explain that in a second. And thus, there is this potential vorticity that changes, causing this this meander. Thus, leading into my next question: what is the equation for the conservation of potential vorticity? Any takers?
Because C over H is.
That's the. Yeah, exactly. So, I'm actually going to write this on the board for a second because this is something that I can kind of figure out. So I'm going to use instead of what is that, zeta? I'm going to use my own zeta outlet plus Coriolis force, and so this is potential vorticity, and this is this is the conservation of potential vorticity. Now the reason I'm writing this on the board, not just because I like orange, if everyone can see that, okay, but it's because what they basically say in this paper is that Coriolis force isn't a factor in this. Now I find that kind of interesting because if you look right here, based on this chart, which is probably highly accurate, Coriolis force should be inaccurate. But what they do is in this model is they say, well, okay, we're gonna scale it small enough where Coriolis force isn't actually going to be a part of this model. Remember, they're doing the model. So what they do is they place Coriolis force with this V sub x, and the V sub x is actually the background vorticity from the longshore current. So I'll put that on here, background vorticity from the longshore current. And I'm going to draw an arrow just because I wanted to do one. So the way this model setup works, they want to measure this vorticity change over time. So what they do is they basically take this new model plus the V sub x, which has been substituted over H, and then they put it in from the Eulerian to Lagrangian, or maybe I got that backwards here. So change in time plus the advection term of the perturbations, right? And then you have that times this right here. Okay. So essentially, that's the background for the model. You have the potential vorticity, all right? Yeah, the potential vorticity. And here, you have the longshore perturbations. And what happens is, they balance each other, thus causing this little wavy, wobbly thing that's meandering. Kind of the principle of what they're talking about is happening in this longshore current. So,
Yeah. So the argument is that
Oh.
it's conserved, so that total derivative is 0.
thank you, yes. It's 0. I had it in here, but I wasn't reading it. Is it? That's pretty bad. Well, you know, it's V0. So, let's see. So, model assumptions, which they have quite a few. Actually, the model assumptions are mostly the same ones that we've been talking about this whole class. So, the flat bottom with simple topography makes it easy. So, no beach. So, rigid lid approximation. So, your C side, your eta is constant. Again, the short scale, this neglects the Coriolis, which is the same as we also did for the edge waves as well. It's non-divergent, so your eta is negligible compared to your horizontal fluxes. And let's see, acceleration is driven by inertial terms, which I started that, but I don't remember why now, so I'll probably get to it later. But the other thing is the conservation of mass, which also kind of comes into play here too. It's like, so there's a conservation that's going on here, which has to exist in order for these waves to continue upstream.
Is the rigid lid is something that's new, so.
Oh, I'm sorry.
That's
I thought we did have that for something else then.
we've been talking about surface gravity waves, which would be non-existent with the rigid lid.
Oh,
so.
yeah.
That was with Timor that we had the rigid.
Yeah,
We did,
we've
yeah.
done rigid lid in
Yeah.
the past. Why do you remember why they're doing
We
this?
have, we did do the ridge lid.
Yeah, and why it's okay to do it.
I don't remember from the paper why they did it, but I can look at. Oh, why in computation?
Yeah.
Well, isn't it because of the, it's to get rid of eta, I thought.
Exactly.
Yeah, to get rid of eta.
Yeah.
Because otherwise you'd have to put it in and